Hello, my name is Stephen. I'm a research associate and a PhD candidate at Bosch Research. I'm presenting our paper titled Leveraging Uncertainties for Deep Multimodal Object Detection in Autonomous Driving. This is a joint work with Yifan Cao, Lars Boderbaum, Fabian Tim, and Klaus Dittmeyer. Autonomous vehicles are often equipped with multimodal sensors, such as cameras, lidars, and radars, to perceive the uncontrolled and complex driving environments. Take a look at two common driving scenarios. On the left is a nighttime driving scenario. On the right is an urban driving scenario with different traffic participants. Different sensors have different sensing properties and thus have strengths and weaknesses in detecting objects. In the above figures, I show the car detections from the state-of-the-art deep neural network that uses only LiDAR point clouds. The camera images are only for visualization purpose. The network classifies objects and localizes their 3D positions in a frame-by-frame manner. From these two examples, we can easily see the strengths and weaknesses of LiDAR point clouds and camera images in the problem of object detection. LiDAR sensors can provide us accurate depth information and is robust to light conditions. Therefore, you can see that LiDAR perception during nighttime is pretty similar than during daytime, and we can get very accurate object localization in the LiDAR bird's eye view without occlusion and overlapping between objects. In contrast, you may find it very difficult to recognize objects with RGB camera images during nighttime. For example, the parking cars on the left lane are almost invisible in camera images. However, LiDAR points become very sparse for long distance, making classification very difficult. In the right figure, you can see that the LiDAR detector misclassifies a cyclist with a car due to insufficient LiDAR points. In contrast, camera images capture detailed information of textures and can help to classify objects easily. In this paper, we try to answer the question, can we exploit the complementary properties of different sensors to build more robust and accurate object detection using deep learning approach? In recent years, a lot of methods have been proposed to fuse different sensors in deep neural networks. We refer the interested readers to our review paper listed below. One of the leading fusion networks is MB3D, proposed by Chen in 2017. MB3D is a two-stage network that fuses LiDAR and images. In the first stage, each of sensor modality is pre-processed by its own convolutional backbone network. The LiDAR bird's eye view channel is also used to generate 3D region proposals from a small region proposal network. In the second stage, the 3D proposals are projected into the front view and the bird's eye view in order to extract the regional features from LiDAR and camera data. Those regional features are finally fused together in a fusion network to fine-tune the classification and bounding box regression. In this work, we study how to fuse LiDAR point clouds and camera images for 3D object detection, following the MB3D architecture. Besides, we leveraged uncertainty estimation proposed in our previous works to improve the fusion network robustness, especially when sensors are misaligned. We validated our method on 3 real-world datasets for autonomous driving. In the following, I will introduce our methodology in detail. This slide shows the fusion network architecture. The LiDAR point clouds are represented in the bird's eye view and are processed by a state-of-the-art LiDAR detector to generate 3D proposals. Then, the LiDAR and the camera features are cropped and further processed by a small fusion network with 3 hidden layers, each with only 256 hidden units. We find that such a small fusion network has already produced promising results. The fusion network architecture is designed in a modular manner. For example, we can train the LiDAR branch, the camera branch, and the fusion network separately. We can also easily extend the network with new sensors by adding a new sensor-specific branch and training the small fusion network without affecting the other subnetworks. Next, we introduce uncertainty estimation in this fusion network in several ways. First, we employ our previous method to model uncertainty in the LiDAR branch, because in this way, we can improve the accuracy of 3D region proposals and thus improve the success of fusion network. This is how the method works in details. When we model uncertainty in the LiDAR detector, we assume that the 3D region proposals are Gaussian distributed. We use the network output layers to directly predict the mean and variance of the regression variables, and learn the uncertainty by standard maximum likelihood estimate. Similarly, in classification, we assume that the softmax logit, which is the regression variable for softmax function, is also Gaussian distributed. Its mean and variance are directly modeled by network output layers and learned by maximum likelihood estimate. As a result, the LiDAR detector predicts the probability distribution in classification and regression for each region in the feature maps, which can be visualized by an uncertainty map. Based on the uncertainty map, we propose to propagate uncertainties into the fusion network through a simple sampling mechanism. When training the fusion network, we first sample the region of interests, or 3D region proposals, based on the estimated probability distributions. Then, we train the network with the sampled region proposals. Besides, we sample the softmax scores and concatenate them with region of interest or ROI regression variables as auxiliary proposal features for the fusion network. This simple sampling mechanism brings two benefits. First, it helps to improve the detection robustness as the network learns to handle proposals with different levels of uncertainties. Second, the sampling mechanism serves as a simple data augmentation method that generates more diverse training data. This helps the network to generalize, which is especially helpful when input sensors are miscalibrated. We conduct several experiments to verify the fusion network design and the uncertainty modeling methods. We use the pixel network, a well-performed LiDAR detector, to generate region of interest proposals. As for the image branch, we use the feature pyramid network, which is a common backbone network for image processing. We use the standard average position and a certain IOU threshold to evaluate the network performance. Here are the experimental results. We first verify the fusion architecture design. Here, we do not model any uncertainties. The upper table reports the detection performance in the KITTI dataset using the average position in the bird's eye view and front view image plane. We observe that when we fuse the LiDAR with camera data, we largely improve the 2D image detection performance, showing the benefits of image features. However, we can also observe the underperformance in average position in bird's eye view, because camera features do not encode depth information and may bring negative effect when fusing with LiDAR data. As an ablation study, we also show the detection performance at IOU equals 0.3 in the lower table, loosening the localization threshold. In this case, we observe that the fusion network improved the performance in all criteria. In conclusion, the current fusion architecture improved the classification, but not localization. And this is due to the different viewpoints between LiDAR and camera inputs. A better solution might project LiDAR and camera features in the same plane before fusion. Next, we study the uncertainty estimation performance of the KITTI dataset in different LiDAR ranges. This table compares the fusion network that models uncertainty in the LiDAR network and the baseline fusion network without uncertainty estimation. We observe that modeling uncertainty produces comparable or better performance because it improved the region of interest generation. When adding the sampling mechanism during training the fusion network, we see further improvement in average position, showing that the sampling method helps the network to be more robust and generalize better. We not only conduct experiments in the KITTI dataset, but observe similar results in our self-recorded Bosch dataset and U-Scenes dataset as well. You may notice that the performance for U-Scenes is worse than the KITTI and Bosch dataset. This is because U-Scenes only uses 32-channel LiDAR, whereas KITTI and Bosch uses 64 channels LiDAR. The LiDAR point clouds in U-Scenes are much more sparse and thus much more difficult for object detection. So far, I have shown you how the method works in datasets with good conditions. When deploying a multi-modal object detector online, however, sensor mismatch could occur due to different timestamps or calibration errors, which may largely degrade the perception performance. In this paper, we study the network robustness against the time misalignment. We follow the work by Shin and simulate the misalignment by randomly shifting all LiDAR point clouds in a frame following Gaussian distribution with zero means and increasing deviation, while keeping cameras as efforts. We compare the detection performance among 3 models: the fusion network trained without sampling, the one with fixed sampling, and the one with our sampling mechanism. All models are trained with a clean KT training dataset and tested on the modified corrupted KT validation set. From the left plot, we can observe that at the same shifting level, the sampling method largely outperforms the models without sampling up to nearly 20% average position, or the one with fixed sampling, showing its improved robustness against the noisy data. However, we still see significant performance drop for all models, indicating that the current fusion architecture is not optimal against the sensor errors. To conclude, in this work, we explored a LiDAR camera fusion network for 3D object detection. The network is designed in a modular manner and can be easily extended. However, it has limited robustness against sensor temporal misalignment. Furthermore, we leverage uncertainty estimation in the fusion network. We model uncertainties in the LiDAR branch and show the improvement in average position. We also propagate uncertainties through a simple sampling mechanism and improve the robustness of the fusion network. In the future, we intend to use better data representation in the fusion network, such as pseudo LiDAR projection for camera images. We also intend to conduct a more in-depth analysis in challenging driving scenarios. Thank you.